Everyone, in this lecture we will discuss the problems related to magnetostatics. So first problem here is find the magnetic field at a distance s from a long straight wire carrying a steady current I. Suppose here this is a long straight wire which carries a current I, and we are interested to find the magnetic field at a distance s from a wire. Then suppose here this is a Amperian loop, so this is a Amperian loop. So here the direction of the magnetic field is this, and as per Ampere's law, this B dot dl is equals to mu naught I enclosed, that is line integral of magnetic field is equals to mu naught times the total current enclosed. Then here we can write B dl, and this is equals to mu naught I enclosed. So here dl, when we integrate this circle, then we can write B, and if we integrate this is a 2 pi s, and this is equals to mu naught. As per our problem, we have a steady current I, so I enclosed is equals to I, so we can write magnetic field is equals to mu naught I over 2 pi s. Okay, so this is the magnetic field at a distance s from a long straight wire. Then we have a second problem. In this problem we are interested to find the magnetic field of an infinite uniform surface current K equals to Kx cap flowing over the xy plane. So as per our problem, suppose here this is a y-axis and this is a z-axis, and here suppose this is a x-axis, and suppose this is a uniform plane. So here as per our problem, surface current K equals to Kx cap. Now here suppose we have this is a Amperian loop, this is above the plane, and here suppose this is below the plane, and suppose here length is L. So this solid line show above the plane and dotted line show below the plane. So this is nothing, this is again a Amperian loop. Okay, so first point here is the direction of magnetic field. So direction of magnetic field is along y-axis. Okay, so direction is along y-axis. Then according to Ampere's law, again here B dot dl is equals to mu naught total current enclosed. So here we have this B and this is a dl, and as per our, and this is equals to mu naught I enclosed. So here when we integrate this, so as we discussed, this is a Amperian loop and length is L. So only the top and bottom of the length will contribute, and this portion will not contribute in the total integration. So as a result, we get in play we get 2L. Okay, and as per our problem, here K equals to, that is a surface current K is equals to Kx cap. So we can write a mu naught in place of a K, or here because length of Amperian loop is L, so we can write KL. Why it is so? Because I enclosed, this is equals to K x cap, or as per our problem, because we have Amperian loop having length L, so we can write KL. So B to L equals to mu naught KL. L is cancelled with this, so we can write B equals to mu naught K over 2. So this is the magnetic field. Okay. Now more precisely we can write B is equals to plus mu naught K over 2 y cap for z less than equals to 0, and this is minus mu naught K over 2 y cap for z greater than 0. Okay, clear? So here the field is independent of the distance from the plane. Next, in the next problem, we will find the magnetic field of a very long solenoid consisting of n closely wound turns per unit length on a cylinder of radius r and carrying a steady current I. So as per this problem, suppose here this is a solenoid, and these are the wires wound on this, and here suppose this current is I, this is the direction of the current, and here this is a current, this is the direction, and suppose here as per our problem this radius is r. Now first point here is related to the direction. So as per right hand rule, direction of magnetic field is upward, direction of magnetic field is upward inside the solenoid, and downward outside the solenoid. Okay, so first point here is direction of magnetic field is upward inside the solenoid and downward outside the solenoid. And next point here is, so as we move away from we move as we move away from solenoid, B is approaches to 0. The magnetic field approaches to 0. Okay, so this is related to the direction of the magnetic field in case of a long solenoid. Now here, suppose this is a solenoid and these are the wires, and suppose here we have a one loop which is a half this is a rectangular loop, half inside the solenoid and half outside the solenoid, and suppose this is a loop number 2, and suppose we have a similar loop which is altogether outside the loop, and here this is a loop 1, and suppose the length of this loop is L. Now here, suppose this is a center point of this solenoid, then the distance of this from this is A, and from this to this is B. Okay, so now for loop 1, so again we will apply the Ampere's law, that is B di is equals to mu naught I enclosed. So when we integrate, then what we get B A, limit to limit is A, and this is B, and here we have a length of the loop, and this term is equals to 0 because current outside solenoid is equals to 0. So here but L not equals to 0, so magnetic field BA is equals to BP. Okay, so it shows that field outside the solenoid does not depend on the distance from the axis. So first point here is the magnetic field does not depends on the distance from the solenoid when we are outside. And second point here is, as we move away from the solenoid, the magnetic field approaches to 0, or we can say it must be 0 everywhere here. So next point here is for loop 2. So here, as per Ampere's law, B di is equals to mu naught I enclosed. So here we have, because this is an integral, this is di, and this is equals to mu naught I enclosed. So here only this portion will contribute, that is, this is length will contribute, because this is outside, so it will not contribute here. So we can write BL is equals to mu naught I enclosed, here is N I L. So N is the number of turns, I is the current, and L is the length of the loop. So L is cancelled with this, so we get B equals to mu naught N I. Okay, or finally we can write this B equals to mu naught N I Z cap this is for inside the solenoid, and this is equals to 0 for outside the solenoid. Okay, thank you.